So a good place to start on a question that involves a number of forces is to draw a free body diagram. So we would think about that box's mass being squashed all down into one little point, and then we would start labeling some forces. Anywhere there's contact, there's going to be a force. So we would have this pulling force, maybe we call it F sub t, that's at an angle, theta. We have a normal force, that's what we're talking about here. And that would be upward since our surface is down below our object. And then also because there's a surface in contact and there's mention of friction, we would include that. Our object is going to be moving to the right, and so our frictional force working against that sliding motion is going to be a kinetic friction pointing to the left. And then lastly, the force that doesn't need contact, that's the gravitational force pointing down. And so what we would do here is we would consider all of these forces, but we would consider them in terms of what's pointing horizontally and then what is pointing vertically. And so any force that points vertically, those are going to have to balance out because our object doesn't actually move. There are these two forces, F of n and mg, that are shown here, but there's also an upward component of the tension along with a horizontal component of the tension. And so we're going to have to break the tension force into two pieces so that we can use it within our calculations. Give myself a little more room here. All right, so let's look in the y direction. All the forces in the y direction actually have to balance out. They're going to have to equal 0 if I take into account their direction. So that means that F of n plus this component upwards, that's going to be the hypotenuse times the sine, so F of t sine of theta. That all pulling upwards is going to have to equal the weight that's pulling down. If I go through and put some numbers in here, F sub n plus my tension force is 160 times the sine of 25, that will equal the weight down, which is 20 times 10, or 200 newtons. When we go through and do this, we should get 132 as our normal force, so a little bit less than the weight itself. Then if I switch directions and I look at the x direction, I should be able to find my acceleration. These forces don't add up to 0. They add up to the mass times the acceleration. Again, thinking about the direction of things, since the acceleration is to the right, then I'm going to choose the rightward force to list first. That's my positive force. So that would be F sub t times the cosine of theta. Working against the motion is the frictional force, and friction is mu times the normal force. So we'll put that in as mu times F sub n. And together, that all determines the mass times the acceleration. Again, putting in some values here, I have my tension of 160 times the cosine of 25 minus mu has a value of 0.2 in the problem, and then I'm going to use this normal force that I just found, 132. Mass is 20, and then times A. And this comes out to be about 5.9. Again, key points to this problem. You gotta make sure that you're looking at the everything going on in the y direction, everything going on the x direction. Keep all of your components separate, solving sort of two problems within one. All right, the second question, I'm not actually going to go through and solve completely. I just want to point out some differences that we would see. So because the boy is pulling somewhat down on the rope, my tension force would look something like that. I would still have the weight force of mg. That looks like a 35, 55 here. I would still have normal force, but since the tension force has a component to the right and a component down, I expect my normal force to be much bigger than in the last problem, because the normal force is going to equal the weight plus the component of tension that's pulling down. And then, of course, I would have a frictional force as well. So you would go through and do the same sort of setup as you would in other situations. But again, paying attention that your applied force or your tension force is somewhat down. If you want to pause the video for a second, I am going to post the solution here so that you can see it, but give you a chance to try this question on your own. All right, so hopefully again you pause the video and tried it on your own. Key things to notice again is that this step changes a little bit. You got to look at your picture, use that to determine how the up forces are going to balance out the down forces. And then also notice here, played around a little bit with the angles. You certainly could use the cosine of 55 here and the sine of 55 here. I just prefer to work with angles with respect to horizontal.